Hi everyone. In the previous lectures, we introduced the idea of a differential amplifier. We also introduced the idea of a differential signal. We said a conventional single-ended signal is normally a single-ended small signal is normally measured with respect to some AC ground. So the node voltage here will have some AC variations with respect to a ground which remains calm. So there is no ground will not have any variations, AC variations. In case of a differential system or a differential signal which normally occurs in differential amplifiers, you have two terminals. Now the voltage at these two terminals will be exactly 180 degrees out of phase. So if this increases by plus delta V, V minus will decrease by minus delta V. So then these two nodes, we said they are differential nodes or nodes in a differential system. So that's what I have shown here. So whenever we have a differential system, then we said we can define two kinds of voltages. One is the difference between the two voltages and the average of the two voltages. The difference, we called it as the differential voltage between the two terminals, and the average is what we called the common mode variations in the two terminals. If both the terminals increase by delta V, then we say that the common mode variation is the average is delta V as well, So I've shown here a single-ended amplifier with a single-ended signal, input signal, and a single-ended output signal. And I've shown a block diagram representation of a differential amplifier, which we said, we discussed how do we construct a differential amplifier, as we took two identical single-ended amplifiers and formed a differential amplifier by feeding inputs differentially and by taking outputs differentially. So in this lecture, we are going to look at how do we characterize a differential amplifier. For a single-ended amplifier, of course, leaving aside the input and output resistances, the most important parameter in a single-ended amplifier is the voltage gain itself. So that's the voltage gain for which we design an amplifier for. But in case of a differential system, in case of a differential amplifier, you have differential signals and common mode signals. Therefore, we have to now start defining different gains in a differential amplifier as opposed to a single voltage gain in a single-ended amplifier. So that's what I've shown here. So for a single-ended amplifier, voltage gain is sufficient. And we said the problem with a single-ended amplifier was that if there is any noise on the supply or if there is any noise on the ground, they can directly appear at the output. And we said that a differential amplifier, if you apply inputs differentially and take the outputs differentially between the two terminals, when I say differentially, I am referring to outputs measured between two terminals which exhibit a property that they both are 180 degrees out of phase in the small signal sense. Then the common mode noise because of the supply and ground can be completely eliminated, rejected. So now, how do we measure how good a differential amplifier is? So for example, a differential amplifier, unlike a single-ended amplifier, should not only amplify the differential signals, but it should also reject the common mode ground and supply variations. So are there any metrics that we can define for a differential amplifier which tells me how well it can reject some common mode or supply variations? So that's what we'll do in this lecture. We'll try to define the different gain parameters that one normally uses in a differential amplifier system to characterize it. The first one here shown here is AD. It's the differential gain itself. I'll briefly explain it in a few moments. So this is the actual gain of interest. So because your input signal is differential, output signal is also differential, the ratio of output differential to input differential will be your differential gain. The second thing is ACM. ACM is the common mode gain. So you're going to feed a common mode input. So which means in a differential system, you're going to ensure both the inputs are the same. and see how both the outputs are responding in response to that. So you'll take the common mode output and common mode input and take the ratio. So that's called a common mode gain. As I'll explain in a few moments, when we talk about the common mode and differential gain, you might think they look very similar, because after all, a differential amplifier is normally built using two single-ended amplifiers, two identical single-ended amplifiers, and I'm going to measure the common mode by applying same inputs at both the ends. And generally, if you see a differential amplifier, let's assume it was built using two identical single-ended amplifiers, one would expect that in case of a differential gain, so if I apply Vi here and I'm going to apply minus Vi by 2 and plus Vi by 2, so then the output is going to be A times Vi by 2, and here it's going to be minus of A times Vi by 2. If I take the output differentially, I'm going to get A times Vi as the voltage gain, as the output voltage, so voltage gain is simply A. But now, if I apply a same input, so I'm going to apply VICM and VICM at both the inputs. So this is a common mode input, and see how both the outputs respond to that. So this is going to be A times VICM, this is also going to be A times VICM. So the average at the output, that is VO plus plus VO minus by 2, will also be A times VICM. So now if you see, the common mode gain here is A, which is exactly the same as the differential mode gain. So the intuition should be that if an voltage amplifier, a differential voltage amplifier, is built using two identical single-ended voltage amplifiers, then shouldn't the common mode and differential gain be exactly equal? We will see that's not always true. Okay, so that's why this is an important parameter. We will see in what cases that a common mode and differential mode gain will not be the same, which is why I discussed at length in the previous lecture about the idea of a differential gain, a differential ground. So we will see that when we analyze more complex circuits at a later stage, we will see that this will not be the case for many circuits. And the third and the most important parameter is ACMDM. So this is the differential mode gain for common mode inputs. So this is important because your circuit should not respond differentially when you apply same inputs at the input terminal. So this also is a measure of how symmetric the circuit is. I'll talk about this in more detail when we start discussing, when we start analyzing these parameters in more detail. So first I'll mathematically give the equations for these three parameters for a differential pair. In any differential system, we will always have two nodes which are going to have opposite variations as far as with respect to some AC signal. I can generally write V plus and V minus as two differential signals. Then this can be input, output, or some intermediate node in a differential amplifier. I can generally write V plus, one of the positive differential output, as it will have a DC content, which I am representing it as capital VCM. It will also have a small signal component, small VCM, which is same to both the inputs, both the nodes. And it will have a differential component, here I have denoted it as V by 2. Now if you see V minus here, so which is the other differential node in the differential system, it will also have the same DC component VCM. It will also have an exactly the same small signal common mode component, small VCM. And the differential component will have different polarities. If it is plus V by 2 here, it's going to be minus V by 2. Now what is the small VCM? The small VCM here can be a common supply noise, or it can be an amplified version of the input common mode noise. You can have some common mode noise at the input at both the terminals, which might be amplified, and it will appear as common mode at that node. Now, so keeping that in mind, I have written some general definitions for the input signal differential inputs. So Vi plus can also be written as VICM, input common mode small signal, and input common mode level. VCM is the capital VCM is the DC input common mode level. Then we have the small signal differential input, Vi by 2. So if you see Vi minus, the first two terms will have same polarity because they both are common mode, and the last term indicates the differential component, which will be exactly 180 degrees apart. Now if I am talking about small signals, when we talk about small signals, then I'll ignore the DC component and simply say Vi will contain VICM plus or minus Vi by 2. So this will be the two differential voltages at the input. Similarly, at the output, I can define the AC levels as VOCM, small VOCM, as the small signal common mode component, and V0 by 2 as the differential voltage or the differential component of the output voltage. So you can see similarly for VO minus, VOCM is common and the inputs are 180 degrees out of phase. So then the differential gain is defined as the ratio of the differential output, VOD. I am calling it as the differential output as VOD, which is nothing but VO plus minus VO minus, that by the differential input, so which is Vi plus minus Vi minus. This is the actual gain of interest. This is the gain that we are designing a differential amplifier for. In a differential system, the input signals are generally differential in nature, which needs to be amplified. So therefore, this is the gain for which we are going to design this amplifier for. The next parameter is the common mode gain. So in case of a common mode gain, I am going to short the two inputs and apply a same input VICM. And at the output, I can either short it or I can simply see how both the nodes change. If both the nodes increase by delta V0 and delta V0, then the common mode output voltage is the average of the two, which will be delta V0 itself. So this, we are going to see how the system is going to respond for common mode inputs. So here the first response is ACM, which is called as the common mode gain. We are seeing how well the output responds to a common mode input. So VOCM, which is the average of the output signals, which is VO plus minus VO minus by 2, by VICM, which is the average of the two inputs. So here both the inputs are VICM, so the average is also VICM. So this is your common mode gain of a differential amplifier. The third gain is what we call ACMDM. So this is the differential mode output for a common mode gain. So we are going to apply same inputs at both the input terminals, and we will take the output differentially. And we'll take the output differentially and see what will be the output voltage in response to a common mode input. For a purely differential system, we discussed they always exhibit an axis of symmetry around an axis of symmetry. If that is true, if for a purely differential circuit it is going to be purely symmetric around some point, then for such circuits we can say this term will be 0, because if you are applying common mode inputs, both the inputs are going to rise in the same way, so differentially there will be no response. So in fact, we will later see, in the presence of some non-idealities or some unwanted errors, we will end up seeing that you will have a finite ACMDM. So ACMDM is also a measure of how symmetric the circuit is. For a purely symmetric differential amplifier, you will get ACMDM as 0. So it's also a measure of how symmetric the differential amplifier is. So these are the three important parameters to characterize a differential amplifier. And I'm going to take an example to solve and find these three parameters. The circuit shown here is a simple differential pair with voltage biasing. So a DC voltage of VCM is applied at both the gates, and the source node voltage is connected at a DC voltage of VS. Now we are supposed to first find the differential mode gain for this circuit. So since it's a differential gain for small signals, I'll short circuit all the DC sources. and draw the AC equivalent. So my goal is to find the differential output. So this is VO plus and this is VO minus. So divided by VI minus VI minus, VI plus minus VI minus. So VI plus is Vs by 2, small signal part, VI minus is minus Vs by 2. So the differential input is Vs, VID is Vs. Now we'll have to find out the differential output. For that we can directly draw the small signal model. So this node here will come to AC ground, and these two nodes will also be at AC ground, supply will also be at AC ground. So that's what I've shown here. So after drawing the small signal AC model for the differential amplifier, the first amplifier here, the input fed to that is Vs by 2, and I've called it as this node as VO minus as the drain terminal of the first amplifier. So VO minus here is simply, it's a common source amplifier with R naught as infinity, so it will be minus of GMR into Vs by 2. The negative sign comes because it's a common source amplifier. And in this amplifier here, the gain is going to be, the voltage at the output is going to be plus GMR into Vs by 2, because the input signal is negative here. So differentially, the differential output VOD, which is VO plus minus VO minus, is going to be GMR times Vs. So the differential gain is differential output divided by the differential input. That's simply equal to GMR. So that's the differential gain of this differential amplifier we showed in the first example. Now we are going to calculate the small signal common mode gain for this amplifier. So I've applied same input VCM at both the inputs, and we are going to measure what is the average value at both the outputs, how this amplifier responds to this common mode input. So again we will start with a small signal model, so which is what I've shown here. The DC source is at AC ground, these two nodes are at AC ground, and the supply is also at AC ground, so we get the small signal model as this. Now if you see here, these both are identical amplifiers with identical inputs. Therefore, their outputs are also going to be exactly the same. So VO plus and VO minus will simply be equal to minus of GMR, which is the gain of this amplifier, times the input, which is VCM. So the average value, VOCM, the output common mode is VO plus VO minus by 2, will be equal to minus of GMR's VCM. So divided by VCM, you get the common mode gain as minus of GMR. If you noticed, an interesting property here is that, an interesting result to note here is that the common mode gain is exactly the same as the common mode gain in the previous example. The common mode here, in the differential gain in the previous example. So this is what I was discussing a few moments ago when I was discussing the first problem. When I was introducing the different terminologies, I said generally differential amplifiers are built using two identical single-ended amplifiers. So this is supply. So if they are built using two identical single-ended amplifiers, if I apply both same inputs at both the inputs, okay, then the output should also change in the same way. Okay, so and therefore we said in case of differential gain, generally should it not be true that differential gain should exactly be equal to the common mode gain. In this example which we considered, the common mode and the differential gain happens to be exactly the same. We will later see for some very interesting circuits, because of the virtue of differential ground, you will see very different gains for both common mode and differential mode. So finally, to finish the discussion, we will now see the third important gain, which is ACMDM, which is the differential mode output for a common mode input is ACMDM, which is you should take the output differentially and apply a common mode input after applying a common mode input. Now we just saw here both this is equivalent to applying same inputs to two identical amplifiers. If I am going to subtract the outputs, so if I am going to take the output differentially, which means I am subtracting the two outputs, then it will be 0 because both the outputs are changing by the same way. So I have shown in this example, it's going to change by the same way. then it has to be 0. Now this we can argue for a purely differential amplifier. For a purely differential amplifier, when I say purely differential, it's purely symmetric around some axis of symmetry. Then for such an amplifier, I can always say that ACM DM will be equal to 0 or minus infinity decibels. So in the next lecture, I'll take a few more examples and solve and find these gains, and then we will introduce the idea of differential half circuits, which will enable us to solve the problems much faster. Thank you.